So we will continue now. So we are after the concentrations this time. If we will complete, or we have a complete concentration values here, we'll be able to determine the flux that the problem requires from us. So anybody here who knows how to determine the concentration of helium? How do we determine the concentration of helium? So we are after the concentration at point 2 and the concentration at point 1. How do we go about finding this concentration? Anybody? Any suggestion? Okay, the problem gives us the partial pressure of helium at point 1 and point 2. We cannot use the partial pressure because the problem, or the formula rather, requires us to input the concentration. So what do we do? What do we do in order to find the concentration given the partial pressure? So if you recall your thermodynamics, PV is equal to nRT. So concentration, so P over RT is equal to N over V. So your concentration, this N over V, is equal to partial pressure over the product of the universal gas constant and the absolute temperature. Okay? So now we can solve for the concentration at point 2 and point 1 using the partial pressure. So for CA2, I will use the partial pressure of helium at that point and divide it by RT. So your partial pressure for helium at point 2, as stated in the problem, is 0.2 atm. So we cannot make use for now with the raw data because the unit is in atm. So there's a need for you to convert atm to Pascal so that we'll have it in SI. So 1 atm is 101,325 Pascal. Okay? And we divide it. What happens to me when I write? It's going up. So what should be the appropriate R here? If we have Pascal ATM, so I cancel the ATM now. And if my temperature, the temperature that is given in the problem is 298 Kelvin. So what would be the appropriate R to use? What do you think is the appropriate R to use in here? That would be the 8314 Pascal per mole Kelvin. So I get to cancel the Kelvin and I get to cancel the Pascal unit. So I will have pressure. Sorry, this should be Pascal cubic meter. I lack the unit for volume. So your CA2 is now having the value of, can anybody compute? The unit will be now mole per cubic meter. Your CA2 will have a value of, don't have my CA2 value here. What's your CA2 value? Point 2, you multiply to 101,325, you divide by 298, and you divide by 8314. That would be 8.718 times 10 raised to negative 3. The same thing is true for CA1. So in CA1, you will need to use the partial pressure at point 1, and that's 0.6 atm again convert this to Pascal for the SI unit. So we have 1 ATM. We cancel this and we divide by R 8314. Sorry. This should be 8314 times 298. So actually the same, they have the same divisor. I could have just simply placed in the formula. Anyway, your concentration in this case would be 0.6 times 101,325 divided by 8314 and divided by 298. So the concentration at point 1 is 0.025 mole per cubic meter. So now I have the two concentration values. In here, I can substitute. So if I will substitute sheet number 3, so the flux will be given by negative. So we will get the diffusivity, molar diffusivity. In that case, the molar diffusivity as given in the problem is, where is that? 0.687 times 10 raised to negative 4. 0.687 times 10 raised to negative 4. The unit is meter squared per second. This diffusivity will be multiplied to the difference in concentration. So your concentration, plus, our concentration 2 is 8.18 times 10 raised to negative 3. You subtract the concentration at point 1, which is 0.025. And we divide it by, based on the formula, by the distance. Now, this distance as given in the problem from point 1 to point 2 is 0.2 meters. That's the delta Z. So this should be 0.2 meters. Now we have, so this one has a unit of mole per cubic meter. So now we have to cancel meter squared. This one has still 1 meter left. So this goes down and then you have here the per second. So meter squared per second true to the unit of the flux. In this case, your answer would be, we subtract this one from 8.18. We multiply by negative 0.687. And we divide by 0.2. So we have a 5.619 times 10 raised to negative 6. This should be, this should go down per meter. So this is mole per meter squared per second. And that's our flux in SI units. So if it's in CGS units, all you have to do is convert the meter squared to centimeter squared. So if this is one answer that you have, you just convert by multiplying this to 1 meter equal to 100 centimeter. Then we need to square it. So in the CGS system of units, this would even be smaller. And by the way, this should not be negative already, because this one is negative, and negative, that would make it positive. So this would be now 5.619 times 10 raised to negative 8. No, plus 4, negative 10. Negative 10. Mole per centimeter squared per second. If we want it in kilomole, this would even be smaller. So this is in the CJS units of measurement. Your flux, that is. The flux of helium to nitrogen in the stationary mixture of the two. So 5.63 times 10 raised to negative 10 and 5.63 times 10 raised to negative 6. Why is this different? Wait, 5.60 times 10 raised to negative 6, it's in kilogram mole. What's the difference of my units from the one? Is my 8.314 correct in unit class? Is this in mole here or per kilomole? Let me check in the conversion because the problem has an answer in the book and it's in kilomole. It should be in kilomole. The 8314. Wait lang. This will not take long so that our units will be acceptable. The R is the R. 8314. Okay, class. So I stand corrected. That explains it. This should be in kilomole. Okay? The 8,314 is in kilomole. So the resulting unit here is kilomole. Kilomole. So same thing here. So you have to be careful with your units. So this should be kilomole. This should be kilomole, kilomole. Now, if this is in meters, if this is squared, 4, negative 10. So kilomole per centimeter squared. Wait, class. So that explains it. If you have here CGS, this should be in grams. Plus, this should be in grams. So my conversion is not full. I'd like to convert on the other side. So your flux in the CGS measurement is 5.62 times 10 raised to negative 10. This is still kilomole per centimeter squared per second, Juliana. And we convert the kilomole to gram mole. So you have 1 kilomole to 1,000 mole, or that's your gram mole. So if you cancel the two, then this will now be in agreement with the answer in the textbook. 5.62 times 10 raised to negative 7. So that would be now mole or gram mole per centimeter squared second. Because if it's CJS, I forgot that your kilo mole or kilogram should be in grams. So this should be gram mole. So this should be the other answer that is being sought after. The flux in terms of the CGS unit is this, whereas in terms of the SI unit would be this one. So if you notice, this problem is a matter of substitution to the formula. The general formula for Fick's law, which we have just simply derived using separation of variables in differential equation. Now, again, this problem is for a stationary solution of the two gases or mix of the two gases. So they're not moving. The entire bulk mixture consisting of helium and nitrogen is not moving. Okay, so any questions so far with this? No question with this? So if there's no question with that, I'll go to the slide. Okay, we'll go back to the slide. Okay, so that's the first sample problem that we have, a simple substitution to the general equation by Fick's law. Now we go to the equimolar counter diffusion of two gases. So in this scenario, John Kuplis in his book in figure 6.2-1 gives you a diagram of two gases A and B at constant total pressure P into a separate chambers. So you have here this chamber 1 and you have this chamber 2, and these particular chambers are connected by a tube where molecular diffusion at steady state is going to occur. Now, in here, what happens is you have diffusion of A from this particular section 1, let's say if this is section 1 to section 2, given that the concentration in section 1 for A is greater than the concentration in section B, or since we are talking about gases, the partial pressure of A in section 1 is greater than the partial pressure of A in section 2. Now, it's counter diffusion in the sense that we can readily, of course, deduce that it must be that the concentration of B in section 2 must be higher than the concentration of B in section 1. That way, our diffusion would be from a region of high concentration to a region of low concentration. And for the two gases to have, shall I say, counter current diffusion or counter diffusion. Since this part is higher in concentration or partial pressure for A, the movement is from left to right. Since this part is higher in partial pressure with respect to B, the movement will be to the left side. So this one is to the right, this one is to the left. So how do we account, in this case, the flux for these two gases moving in counter diffusion? So take note, it's equimolar. So at all times, equilibrium is existing between this system. It is existing, equilibrium is existing, but it doesn't mean that there's no movement. It's just that the species that moves to the right is just the same as this species that moves to the left, and as such, the concentrations at any time between, let's say, chamber 1 and 2 are equal, or shall we say, they are in equilibrium. But of course, the process of transferring or the process of counter diffusion is an unending process, only that the rates are just the same. So now we have a sample problem in here regarding counter diffusion of gases. So ammonia, which is represented as A, is diffusing through a uniform tube 0.10 meters long containing nitrogen, which is B, at 1.0132 times 10 raised to 5 Pascal pressure and at a temperature of 298 Kelvin. The diagram is similar to the one that was shown to in the previous slide. At point 1, the partial pressure of A is 1.013 times 10 to the 4th Pascal. And at point 2, the partial pressure of A is 0.507 times 10 raised to the 4th Pascal. The diffusivity of A to B is 0.230 times 10 raised to negative 4 meters squared per second. This is our molar diffusivity of A to B. You are asked to calculate the flux of A at steady state, and you are to do the same with the flux of B. Let's see if the two flux of the two species are the same, since it says that this is a system that is said to be at equilibrium. So it's at equilibrium because it's equimolar. So equimolar counter diffusion. So if there are equal amounts of moles that transfer from both sides of the chamber, then of course equilibrium is established or maintained in the system. So we'll transfer again to the board. And this is for our second problem. So we will write down what we are provided for in this problem. Actually, this is taken also from John Copley. So we have A, and we will label that as ammonia. And B is nitrogen gas. Okay? From the first statement, we get that A is ammonia and B is nitrogen, and that the tube where that connects the two separate chambers containing these two gases is 0.1 meter long. So let's say this is our delta Z, 0.10 meters long. So the tube that is containing the two. Um, the partial pressure of B, where A is to diffuse into. So partial pressure of B is 1.0132 times 10 raised to 5 Pascal. Ammonia gas is diffusing through a uniform tube 0.10 meters long containing N2 gas, which is B, at 1.0132 times 10 raised to 5 Pascal pressure. And this is happening at a temperature of 298 Kelvin. Okay, that's in the problem. The manner of diffusion is the same as the diagram that I have shown to you a while ago. And from point 1 in the diagram where A is to diffuse, transferring to B, to point B, the partial pressure is 1.013 times 10 raised to 4 Pascal. And then at point 2, we have 0.5, we'll have this equal, 0.507 times 10 raised to 4 Pascal. And then we're given the diffusivity of A to B. In this case, we are given 0.230 times 10 raised to negative 4 meters squared per second. Now, the required information is we calculate both flux. And let's see whether they'll be the same. So we go to the solution. Now our formula will be the one that we'll be taking from the integration that we did from the fixed law. So I will just copy from that. And this is the formula that we have, this one. So I will copy that here. You will not do again, start from the DE. So we'll go straight to the derived formula. So GA, and that would be negative DAB. Then we have concentration over, I will just place this one as delta Z. Now, if you recall, I have converted the partial pressure, since it's partial pressures that are given, into concentration. So in terms of partial pressure, this concentration can be written as, so we copy the molar diffusivity. And based on the formula that we got a while ago, this one is PA1 over RT minus PA2 over RT. And we have delta Z here. And again, I'll write here negative DAB. I will have simply the partial pressures here on top. And since both are divided by RT, I'll place RT at the denominator and multiply it by the distance traversed by A into, so that it can diffuse to B. So I will get this negative, double negative already. So this is it. So what I'll do, I will substitute the partial pressures that we have. So in terms of the diffusivity, so the problem gives us that it is 0.230. So negative 0.230 times 10 raised to negative 4. What's that? Negative 4. Okay. Meter squared per second. And in terms of partial pressure, the problem gave us that the partial pressures are already in Pascal. So it's okay. So I will have 0.507 minus 1.013 all raised to negative 1.013, both multiplied times 10 raised to 4. So this is Pascal. We divide by 8314 Pascal cubic meter. Take note, this is kilomole Kelvin. And we have the temperature, which is 298 Kelvin. And we have the delta C, which is 0.10. So we place here 0.10. So you can now have the flux of A. So the flux of A in this case, I will just copy what is provided here. It's 4.7 times 10 raised to negative 7. So unit is kilomole per meter squared second. So that's A. Now when we speak of B, it's actually the same formula, but you will have a different partial pressure to substitute. So we have here still a 0.230 times 10 raised to negative 4. And this time, the partial pressure of B would be computed based on this premise. So if you notice, I'll read the problem again. The total pressure of the system is 1.0132 times 10 raised to 5 Pascal pressure. So this is the total pressure of the system. So if your A is already given at 0.1 to be that particular partial pressure, then this partial pressure of B will be the difference of the total pressure here of the system and the partial pressure of A. What I mean is this. So I know you can see the slide. So in terms of the partial pressure of B at 0.1, what you need to do is, I'll leave this blank for now because this is PB2 minus PB1, and you still have here the 8314. I will not anymore place the unit, and this is still 0.10, just like in the previous calculation. Okay, then 298. I forgot the 298. So you have here the 2, so 10 minutes again. So this is 298. Now, this remains to be determined, the partial pressure of B. So let's say this is equation 1. So you have partial pressure of B at 0.2 will be the total pressure of the system, which is 1.0132 times 10 raised to, what was that? 5. By the way, class, this is not the partial pressure of B, but rather the total pressure of the system. Okay, I'll erase that. This is total. Okay. This is the total pressure of the system, PT. Times 10 raised to 5, that is, this is 5. And at 0.2, if you go back to the given, the partial pressure of A is 0.504. So we will subtract it there. 0.504 times 10 raised to 4. Was it? 504. 507 times 10 raised to 4. So this is 7. 7 raised to 4. And you do the same with partial pressure of B at point 1. So 1.0132 times 10 raised to 5 minus, minus that of A at point 1. So A at point 1 is 1.013 times 10 raised to 4. Now we will now substitute these two in the equation above. So you have negative, you have 0.230 times 10 raised to negative 4 times. So if you process this, that should be the value. This one is 96250. This one is 91190. So we'll have 96250 minus 91190. And we have this 8314 times 0.10 times 298. Our answer should be the same as the one we have on top, only it's negative because they are opposite in direction. So let's see, 0.230 exponent negative 4 times quantity 96250 minus 91190 divided by 8314 divided by 0.10 divided by 298. So this should be times 10 raised to negative 7. The same as our answer on top. Negative 4.697 times 10 raised to negative 7. Same set of units, same value, only that the sign is negative. Don't make it positive. It should really be negative because this time it's B diffusing to A when you determine the flux here rather than A diffusing to B. So the numeric values of the two fluxes would be equal, but they are of opposite direction. So that is why it's negative. Okay? 4.7 times 10 raised to negative 7. Okay? Now, in diffusion class, actually, there are a lot of scenarios. And actually, in this set of slides alone, I have 12 sample problems to be covered. So for tonight, we only covered the 2. I will give you sample problems later on what you will process in your dry lab schedule, but it will not be submitted tonight because I will still have to send it later. I was not able to take it out from the text where I took the sample problems. So you can process it on any of your spare time, anytime tomorrow until Saturday or Monday next week if you want, as long as you comply. But anyway, the problem set will be comprehensive. What do I mean with comprehensive? It will cover the entirety of the topic of diffusion. So it cannot be processed in just one setting tonight and submit right away. Just like the previous problem set that I gave, wherein I need to cover everything first before you can comply in terms of the submission of the solution. So for tonight, you will have only this, okay, these two. I can continue with the next in terms of the discussion of the principle, and that would be, excuse me. Can you still see my slide? Can you see my slide now? I transferred from the sample problem number 2.
Boardless ang makita.
Ang board gyapon, sorry. Okay, so you can see now the slide.
Yes, miss.
Okay, so this is the third topic under diffusion. So we have discussed only the first two. As I've said, there are 12 sample problems for this diffusion topic alone. So this one is the molecular diffusion of A through the stagnant non-diffusing gas B. Now, it's you should be able to differentiate the previous topic from this one under diffusion. The previous topic is both gases are free to diffuse from each end of the chamber. So A is diffusing towards the right and B is diffusing towards the left. Whereas in this scenario, in the third scenario, only A is diffusing because B is non-diffusing. uh, A is diffusing through a stagnant non-diffusing gas B. And the illustration is this one. So an example that is placed here is your gas A diffusing to a non-diffusing B in the case of benzene and evaporating into air. So this is your air, the stagnant non-diffusing air, but benzene is diffusing to it. So this is one scenario. Benzene from this part, let's say, of the tube is diffusing to this part here, point 2, into the stagnant non-diffusing gas air. So benzene is A here. Another sample that's stated here is ammonia in air being absorbed in water in the case of gas absorption. So your ammonia in the air ammonia mixture is being absorbed by liquid water. So in this case, your liquid water is in here and A is transferring from point 1 to your non-diffusing gas B, which is water, or your liquid water in this case. It's not gas, but rather liquid water. So from point 1 to point 2. So this is the third scenario. And for this particular problem, you need to determine the lub mean of the partial pressure of the non-stagnant component B. The lub mean of the partial pressure of the non-stagnant component B. And this is the formula for that. And then the flux will be computed. This is already pre-derived based on this particular formula. It would still be needing the molar diffusivity of A to B. You will be needing the total pressure of the system and the partial pressures of A in point 1 to point 2 where your non-stagnant, your stagnant rather non-diffusing B is. And this is the distance covered by A as it transferred from point 1 to point 2. Your PBM, the lub mean of the partial pressure of B is in here. So you need to determine it using this formula before you can determine the